Our investigative research into the origin and first major use of solid-state diode-detected devices led to the discovery that the first transatlantic wireless signal in Marconi's world-famous experiment was received by Marconi using the iron-mercury ion coherer with a telephone detector invented by Sir J.C. Bose in 1898. The Institute of Electrical and Electronics Engineers, popularly known as IEEE, inducted Bose into its Wireless Hall of Fame. The world recognized Jagadish Chandra Bose as a co-discoverer with Marconi for wireless radio propagation through free space. It was January 1998 when it had been established that Marconi's wireless receiver was invented by J.C. Bose. Marconi used a slightly modified version of the receiving device, the mercury autocoherer, to receive the first transatlantic wireless signal in 1901. Today, radio, television, radars, ground telecommunications, remote sensing, microwave ovens, and internet owe a lot to Acharya J.C. Bose, who discovered microwaves and transmitted signals without wires. He also demonstrated for the first time that plants show response to external stimuli. The only fair estimate of a man comes from an appreciation of the setting in which he lived and moved. Look at his house on Acharya Prafulla Chandra Road today. A small marble tablet, the house number 93, was where Jagdish Chandra Bose lived. With neighbors as Rabindranath Tagore and Swami Vivekananda in the elite neighborhood of the northern part of the then Calcutta. It was a time of intellectual ferment. It was also a time when the atmosphere for research and science was non-existent in India. It is against this backdrop that J.C. Bose began making original contributions to experimental science at a time when no one from this country had yet ventured into the field. While teaching physics at Presidency College, J.C. Bose resolved to become a scientist. It was his 36th birthday, and that was when he showed the possibility of signaling by short electromagnetic waves first at the Presidency College and then at Calcutta Town Hall. Here is a reconstruction of the events. In a small room at Presidency College sat Acharya Prafulla Chandra Ray watching Jagdish Chandra Bose conduct his experiment on microwave propagation. And this is Father Lafont, the legendary teacher of physics at the St. Xavier's College, who stood guard at the door. Behind the closed door lay another room where Professor Pedler sat with his eyes riveted at the pistol. Pressing a key, Acharya J.C. Bose triggered the firing of the pistol in the adjacent room, without the aid of any mechanical or electrical contact. This demonstration in Calcutta showed for the first time that communication signals could be sent through electromagnetic waves. Acharya Jagadish Chandra Bose demonstrated that electromagnetic waves could be transmitted to a distant place through space. His experiments also showed that electromagnetic waves could control a phenomenon occurring at another place. This, in essence, is the remote control system. But what was the significance of such a pioneering work? The first, most important significant event in radio science in India. See, how did this all come about? How did it all begin? It was the Scottish physicist James Clerk Maxwell who predicted the existence of electromagnetic waves on purely theoretical grounds. It can be shown from Maxwell's equations that electric and magnetic fields in an electromagnetic wave are perpendicular to each other and to the direction of propagation. All forms of electromagnetic energy are waves, and as waves, they have frequency. Frequency is usually defined as the number of waves that passes a certain point in a second. Interestingly, electromagnetic waves are different from other waves. Electromagnetic waves could travel in multiple planes in contrast to sound waves, which travel in air as longitudinal waves of compression and rarefaction, whereas waves on the surface of water are transverse waves. After the path-breaking researches of Maxwell unifying electricity and magnetism, there came a German scientist, Heinrich Rudolf Hertz, who first offered experimental verification of Maxwell's theory. He demonstrated that one could produce and detect electromagnetic radiation, now generally known as radio waves, at the time more commonly called Hertzian waves or etheric waves. Well, this is how Hertz had produced Hertzian waves or electromagnetic waves. The spark that you see here are Hertzian waves. Along with the spark, radio waves are also produced. Hertz also showed that electromagnetic waves could be reflected and refracted like light waves. But the shortest wavelength produced by Hertz was 0.66 meters or 66 centimeters. For measuring the optical properties of these waves, like reflection, refraction, polarization, etc., Hertz had to use very large apparatus. But 7 years after Heinrich Hertz's demonstration in Germany, something very remarkable happened. And it happened here in India. Acharya J.C. Bose became the first to fabricate the device that generated microwaves of very short wavelengths, which were from 25 mm to 5 mm. Consequently, his apparatus was very compact and could be carried about in a small box. It was a breakthrough in the truest sense because it was at this time that Marconi, Lodge, and others were using long electromagnetic waves of wavelengths of the order of 100 meters for transmission of messages without wires. Acharya J.C. Bose demonstrated a new type of radio waves as small as 1 centimeter to 5 millimeters, which are now called microwaves. Here is a quick look at what are radio waves and microwaves. As we know, the human eye is sensitive to only the limited range of wavelengths corresponding to the colors red to violet. The spectrum beyond red, which includes radio waves, have microwaves. Radio waves with the largest wavelengths are bounced off of layer high up in the Earth's atmosphere called the ionosphere. The ionosphere enables intercontinental radio transmission around the curved surfaces of the Earth to be achieved as a result of its property of reflecting electromagnetic radiations of radio frequencies. And here is how these radio frequencies in the microwave region, that is as small as 1 centimeter to 5 millimeters, were achieved by Acharya J.C. Bose during the last quarter of the 19th century in his laboratory at the then Calcutta. This is the radiator, also known as transmitter antennae or wave emitter. And this is the point contact detector, also known as coherer. And this is the receiver or receiving antenna, also called the wave detector. And these are the gratings. Here is the high voltage equipment for generating the spark. This screw can adjust the pressure of the point contact detector. The circle is for holding polarizers. In particular, Acharya J.C. Bose showed that short electromagnetic waves behave exactly as a beam of light does, both being amenable to reflection and refraction. He even managed to polarize the electromagnetic waves in order to further lay bare their identity with light rays. He used a twisted bundle of jute and an assembly of paper sheets to show that it could rotate the planes of polarization of electromagnetic waves. These pioneering work in millimeter waves by Acharya J.C. Bose laid the foundation of experimental science in India. A major challenge those times lay in detecting electromagnetic waves. The most efficient way of receiving the waves were yet to be made definite. Just as our eyes can perceive visible light, different kinds of detectors are needed for detecting each type of electromagnetic radiation. And Bose was also faced with such a situation. Receiving the transmitted signal was challenging enough in early 1900. Nothing like a diode existed at that time which could detect the induced signal. How would one then detect a signal? The solution was a device called a coherer. A coherer is a device that detects radio waves picked up by the antenna. The aim of the coherer was to convert the AC RF signal to a DC signal, which can then drive a Morse printer or an earphone. The basis for the operation of the coherer is that metal particles cohere, that is, cling together and conduct electricity much better after being subjected to radio frequency electricity. Unfortunately, the increase in the current persisted even after the radio signal was removed. This was a problem because the coherer had to be ready immediately to receive the next dot or dash. To continuously receive the signal, it had to be tapped mechanically. We will wait just a bit here and see how the French physicist Edward Branly, who invented the coherer around 1890, tried to solve the problem. Branly thought, let me solve it by introduction of a tapper, that is, a decoherer into the system. But the idea did not quite work. After Edward Branly, it was Sir Oliver Lodge who tried his hands at making an improved version of the coherer. But again, it was something which J.C. Bose thought had much scope for improvement. Realizing that good communication needs sensitive detectors, Acharya J.C. Bose further converted the coherers, which were a heap of metal filings in loose contact between two metal electrodes, into delicate spiral spring coherers. This device consisted of sets of tiny springs held together side by side under pressure. When electromagnetic radiation is absorbed by the sensitive surface, there is a sudden drop of the resistance which made the galvanometer deflect. The spring pressure could be adjusted very finely in order to attain optimum sensitivity. This itself was a great improvement on Edward Branly's crude device. Then surfaced a much better coherer than the earlier ones. Acharya J.C. Bose thought, why not use galena, and yes, why not galena, which are crystals of a lead salt, that is lead sulfide. Lead sulfide was just right. Acharya J.C. Bose devised a sensitive receiver out of a pair of galena point contacts, which was the first semiconductor receiver of radio waves. Galena was used to convert electromagnetic waves into electrical pulses, which made an earphone reproduce the sound and one could detect a signal. Nevertheless, J.C. Bose kept working at improving the efficiency of the coherer and eventually surfaced a coherer which was far more superior because it did away with the need for tapping. This ingenious breakthrough device consisted of a small metallic cup containing a pool of mercury covered by a very thin insulating film of oil. Called the iron-mercury-iron coherer, it had above its surface a small iron disc which was suspended by means of an adjusting screw. The lower edge of the disc was made to touch the oil-covered mercury with a pressure small enough not to puncture the film of oil. The action of detection occurred when the radio frequency signal somehow breaks down the insulating film of oil, allowing the device to conduct. This form of coherer is self-restoring and needs no decohering. And this is exactly the scientific problem that Acharya J.C. Bose solved for the world. This special coherer was a huge improvement over any other coherer in use those times. And this was the auto coherer coupled with a telephone which made a robust and reliable receiving apparatus and was eventually used by Marconi in his transatlantic wireless experiment. Having made the device work successfully, Acharya J.C. Bose did not rest on his laurels. He now began to design an improved version capable of functioning at still greater distance between the Presidency College and his own house a mile away. But before he could actualize it, he left for England at the invitation of the British Association to attend its Liverpool session. It was during the course of these discourses, with his free exhibition of all his appliances, that Bose revealed his characteristically ascetic trait that astonished many because he spurned the idea of commercializing his discoveries. One of his American friends, Sarah Bull, also known as Mrs. Ole Bull, was able to persuade Bose to file a patent application for his Galena receiver. The application was filed on 30th September 1901 and it was granted on 29th March 1904. However, Bose refused to accept his rights and allowed the patent to lapse. Acharya Jagadish Chandra Bose was graduate of the Calcutta University and obtained his MA from Christ Church Milton College of Cambridge, Doctor of Science 1896 of the University of London, UK. Was knighted in 1917, elected Fellow of the Royal Society in 1920, born 1858, died 1937. Acharya J.C. Bose would have been glad to see that in the past 4 decades, the microwave techniques he introduced have been successfully applied in many areas in India. But much water has flown down the Ganges since. Continuing with the legacy of first-rate research on radio science in India, there emerged another Indian talent, Professor S.K. Mitra, who worked at the physics department of Calcutta University. Professor S.K. Mitra and his students obtained the first experimental evidence in India of the existence of an ionized layer over India, the E region, in 1903 by utilizing the Calcutta station of the Indian State Broadcast Service and a simple receiving equipment at a distance of 50 kilometers from Calcutta at a village called Haringata. The story now moves a bit further, though with a bit of bad news here. J.C. Bose's pioneering work on microwaves during the turn of the last century lay dormant for some 50 years, until the 40s, when S.K. Chatterjee and his colleagues at the Indian Institute of Science in Bangalore resurrected microwave research in India. But the fact remains that all of them were put on this path by Acharya Jagadish Chandra Bose, the path that he blazed for India and the world image that he brightened up for Indians.